Hi, my name is Yuval Ronen from the Condensed Matter Department in the Weizmann Institute, and in this section I'll talk about experimental realization of the topological superconductivity phase. So in the beginning, I'll remind you a bit what is exchange statistics of fermions and bosons and non-abelian in the context of topological quantum computation, and then I'll scan a bit of realizations of topological superconductivity. Okay, so let's start. So what is exchange statistics? So if you have two indistinguishable particles, you have basically a many-body wave function which describes this initial state. Now when we interchange the position of these two particles, the initial wave function is going to a new wave function. Okay, so in our 3D universe we actually have two species of particles. We have bosons and we have fermions. Now the new wave functions for bosons is just the initial wave function with a plus sign. For fermions, the new wave function is the initial wave function with a negative sign. Now this plus sign and negative sign are actually, it's very small change, but it has deep implication, of course. So the plus sign, for example, gives us Bose-Einstein condensation and gives us stimulated emission. Bose-Einstein condensation, for example, brings us to superconductivity. The negative sign gives us a Pauli exclusion principle, which leads us to the notion of a Fermi sea, which leads us to insulators, metals, and semiconductors. Now, in a 2D universe, we can actually have a full spectrum of particles, and you can think about bosons and fermions as just being at the end of this spectrum. Now, these new quasi-particles are called anion. Now, maybe the simplest anion that you can find is called the Abelian Anion. In the Abelian Anion, the new wave function is again the initial wave function times some phase, e to the I theta. So where can we find these Abelian anions? One place to find them is in the fractional quantum Hall effect in a filling factor of 1/3. Now maybe the more interesting case of the anions is the non-Abelian anion case. Now you can see here that the initial wave function is actually a vector. And this is because the ground state of a non-Abelian anion is basically spanned by many wave functions. It has to be a degenerate ground state. So you should think that your ground state is now degenerate. There is a Hilbert space which is spanning this ground state. And you need to think of your initial wave function as a vector in this Hilbert space. Now when you interchange to non-Abelian anion, you basically make this rotation. So you see now the initial wave function rotated to the new wave function. And this is exactly this multiplication by a matrix. So in the non-Abelian anion case, the new wave function is the initial wave function times some unitary matrix. Now where can you find these non-Abelian anions? So one place to find them again is in the fractional quantum Hall effect at a filling of 5/2. What's the upshot of having non-Abelian anion? So as you heard earlier in the course, this non-Abelian anion can be used in the field of topological quantum computation. So by utilizing this non-Abelian anion, we can create a topological qubit, and this topological qubit will be immune to errors. And this is really the basis for this topological quantum computation field. And this is very desirable because with a topological qubit, you eliminate the need for quantum error correction, which is a major roadblock for quantum computation. Okay, so how can we create this non-Abelian anion? So one way to create them, as I mentioned before, is in the fractional quantum Hall effect, but we can also engineer them. So how do we do that? You can proximitize superconductivity, for example, on topological insulators, on 1D semiconductor which have large spin orbit, or on ferromagnetic atomic chain. Okay, so let's go back to the fractional quantum Hall effect and ask the question, how can you observe exchange statistics? And maybe the easiest answer would be, let's exchange these two quasi-particles with one another and see the effect on the measurement. Now for fermions and bosons, and as we said, when we exchange them, we get a plus sign or a negative sign. Now if we exchange them twice, we will get a plus sign, right? Negative times negative or plus times plus, so we just get a plus sign. But for Abelian and non-Abelian anion, the many-body wave function should change, and this is exactly what we want to measure. Now in the fractional quantum Hall effect, in the integer and in fractions, we basically have edge states which are propagating along the edge of the sample. And by directing this edge state, we can actually make this experiment of exchange statistics. Okay, so how can we direct the edges and create this exchange statistics experiment? So here we use interferometers. and this interferometer basically direct the edges, and then we can make this kind of encircling one quasi-particle around the other. So you should imagine here an edge state which is going along the edge of the sample, reaching the first QPC, and then it can go in or it will be reflected. So this quasi-particle is coming, getting to the first QPC, makes a circle, comes to the other side, and then it can be transmitted to the other side. So this quasi-particle comes, it can make a circle and go out this way, or can go out the other way. But it basically makes a circle in the center of the Fabry-Perot. Now, if you can control and introduce new quasi-particle in the center of this Fabry-Perot, you have exactly the thing which is happening here, that you introduce a quasi-particle and the other one goes around it. So you can basically realize this physics. Now, this is exactly what was done in these two papers in 2009 and 2010 in Charlie Marcus and Moti Heiblum's lab. And what they measured Aharonov-Bohm interference, which is the expected interference, and also Coulomb dominated, but I'm not going to get into it. And this really laid the ground for this kind of experiment. And these days, there are beautiful experiments by James Nakamura and Willett on filling factor 1/3 and 5/2. So now let's go to the other direction of engineering these non-abelian anions by proximatizing superconductivity on different phases. So this engineering idea of non-abelian anions really started from Fu and Kane in 2008, and they coined this idea that the ingredient to create topological superconductivity is that you need helical states, you need a pair of helical states, and you need to induce S-wave superconductivity on these helical states. Now, what are helical states? Helical states are two counterpropagating edge states which has opposite spin. And you need an S-wave superconductor which is nearby this edge state, and you need to proximatize this edge state. Now, if you proximatize the edge state, you open a gap, and this is the topological superconductivity phase. And at the end of this phase, you should get this Majorana zero mode, which have exchange statistics of non-abelian anions. Okay, so now the question is basically, how do we create these helical states with these different phases, topological insulators, 1D semiconductor, and ferromagnetic atomic chain? So let's start from topological insulator. So topological insulators, like conventional insulator, are basically insulator in the bulk. The difference between topological and conventional insulators is that topological insulators have surface states or edge state at the edges of this crystal. So for example, you can see in this illustration that this is a 2D topological insulator, and at the edges of this 2D topological insulator, you basically have these helical states. So you can see here in red the spin down, which is propagating inwards, and in blue the spin up, which is propagating outward. Okay? Now this 2D topological insulator, sometimes referred to as the spin quantum Hall effect, which is basically just another word for the same phenomena. Now mercury telluride was supposed to be the main candidate to be a topological insulator because of the band inversion between the gamma 6 and the gamma 8 band, but there is no gap opening. So basically mercury telluride in its 3D version is not an insulator. So Berneving and Shushang Zhang basically taught us in 2006 how can you make mercury telluride a topological insulator. And there are two ways to do it. One way is to take mercury telluride and to strain it, to take a 3D mercury telluride and to strain it by, for example, growing it in MBE on another material. The other way is basically to make a quantum confinement of the mercury telluride. So what you see here, you see a mercury telluride quantum well with two barriers of cadmium telluride. And when you make this quantum confinement as any well, you open a gap between the states. So what you can see here for a width of a well, which is around 7 nanometer, it's above the, we call it the critical thickness of the well. You see the H1, which is the level associated with the gamma 8 band, and E1, which is the level associated with the gamma 6, and you can see the band inversion. And of course, between them, there is a gap. So this is exactly an example of a 2D topological insulators. And this band inversion between H1 and E1 is what's creating the helical states at the edges of this 2D topological insulator. Now, if you make this quantum well actually thinner, for example, this is a band diagram of a quantum well which is 5 nanometer, then you see that the position of the E1 and the H1 band actually flips. And then we get a trivial insulator, or conventional insulator. So this is conventional insulator and topological insulators. Now, 1 year after, in 2007, Mullenkamp's group in Würzburg actually realized this experiment. So they made a whole bar made out of these quantum wells of mercury telluride with barriers of cadmium telluride, and they measured RxX. So what you can see here, the x-axis is basically the gate voltage, so you change the Fermi level inside this band structure, and the y-axis is basically the RxX measurement. Now, in the black curve, you basically have a quantum well which is very thin, around 5 nanometer, and then you can see that inside the gap, the sample became completely insulator, okay, which is what expected here because this is a conventional insulator. Now, when the thickness of the mercury telluride is around 7.5 nanometer, which is the red curve and the green curve, then you can see exactly the expected value of 2e⁻⁻h, okay, which is a signature of the spin quantum Hall effect, okay? So what you can see here, 1 year later, is exactly the realization of this prediction by Bernavig and Shusheng Zhang. So this measurement showed the spin quantum Hall effect, and we can see by this quantization value the helical nature of the mercury telluride quantum well. And now we need to proximitize superconductivity on this 2D topological insulator. So this is exactly where we go to the prediction by Julia Mayer's group, Julia Mayer and her collaborator, which basically asks the question, what happens when we take a 2D topological insulators and put it between a Josephson junction? Okay, so what you see here is that basically in these two interfaces between the weak link and this superconductor and weak link and this superconductor, we have two Andreev reflection. So you can think about this weak link as actually as a kind of a resonator, like a Fabry-Perot, and you basically have an excitation or bound state, which are called Andreev bound state, between these two superconductors. So you can imagine an electron reflected as a hole, reflected as an electron, which creates an Andreev bound state spectrum. Now the Andreev bound state spectrum looks something like this. And what's unusual in this Andreev bound state spectrum, when the weak link is in the 2D topological insulator or the 3D topological insulator, we see that we have this blue Andreev bound state, which have a periodicity of 4 pi. Okay? Usually Andreev bound state has a periodicity of 2 pi, but now we get a periodicity of 4 pi, and this is because these two states are not opening a gap at zero energy. And this is something unique to this specific weak link. Also, one thing that you can see that the degeneracy of these two Andreev bound state is actually deeply connected to the degeneracy of the ground state that I mentioned, which is necessary for the non-abelian case. If the phase difference between S1 and S2 is exactly pi or 3 pi, you can see that the Andreev bound state spectrum is actually degenerate, which is exactly what's needed to get non-abelian statistics. And this is one of the prerequisites to get non-abelian statistics. But how can we see that we have a periodicity of 4 pi? And this is exactly what was mentioned in this paper. And they offered to do a measurement which is called Shapiro step measurement, which is basically telling us what's the periodicity of these Andreev bound states. Okay, now in 2016, again, Mullenkamp's group did an experiment on 3D topological insulators. Okay, so they realized this idea by taking a 3D topological insulator and strain it on a substrate and putting two superconductors to create a Josephson effect. And then they measured the Shapiro step measurement, and they saw an absence of the n=1 step. This absence of the n=1 step is exactly coming from this 4 pi periodicity of the Andreev bound state spectrum. And this effect is sometimes called the fractional Josephson effect. Okay? Now in the same year, actually, so this experiment was done on 3D topological insulator, But in the same year, Amir Yacobi's group in Harvard did a similar experiment on 2D topological insulator. And what they looked on what happens to the critical current of the Josephson junction. And by looking at the critical current, they were able to show that on the edge state, they have counterpropagating edge state, they have helical states. After their experiment in 2016, again, Mullenkamp group repeated the Shapiro step experiment on 2D topological insulator. So these were basically the beginning, I would say, of seeing topological superconductivity on these materials, which are called topological insulator. Today, people are trying to make a quantum point contact and proximitize them with superconductivity, again, in the hope of seeing Majorana fermions, to localize Majorana fermions, and maybe seeing parafermions also. Now let's move on to the second system, which is basically 1D semiconductor which have a large spin orbit. And this really started by Oreg and Luchin prediction in 2010. And the idea that they brought is basically, if you take a 1D semiconductor, so you can think basically just as a parabolic EK diagram, you need a nanowire or basically a 1D semiconductor which have large spin orbits. So you see the splitting of the spin orbit. This blue and red are basically spin up and spin down in the direction of the effective magnetic field of the spin orbit. And then you need to apply magnetic field perpendicular to the direction of this spin orbit magnetic field, and this opens a gap at the degeneracy point. Now, if you tune your Fermi level exactly to this gap, what you get exactly, again, helical states. So this is how you get helical states in the second platform of the 1D semiconductor, okay? So you can see that when you tune the Fermi level exactly in the gap, you have spin up going to the left and spin right going to the right. Now, if you take this nanowire and you put a superconductor on top of it, then you basically realize exactly what Fu and Kane predicted, which is you open a gap. This is the topological superconductivity phase. And you should have this Majorana zero mode at the edge of this gap. Basically, this is not completely right. You also need to open a gap here to really localize them here. So to sum up, in this platform, you basically need spin orbit, magnetic field. This gives you helical states. And then you proximitize it with a superconductor. Now, 2 years later, the first group that really realized this physics was Leo Kovenoven's group. So what you can see here, this is an indium arsenide nanowire, and with a superconductor, type 2 superconductor, niobium titanium nitride. And what they observed this zero bias peak, what you can see here. And this zero bias peak is exactly what I mentioned. This is the Majorana zero mode. And this zero bias peak actually tells you that your ground state is degenerate. And this is what Yuval Oreg mentioned in the previous section. Now, after this work, there was also another work from Weizmann in Moti Heiblum's lab. And again, you can see here this zero bias peak. This is the zero bias peak in white. And again, this actually system was another kind of nanowires. This was indium antimonide. This was indium arsenide with aluminum superconductor. So this is actually another observation to the same effect on another platform. Then there were also a measurement on Josephson junction by Lund, and also Charlie Marcus made also a measurement on indium arsenide nanowires. So all of these are actually different measurements that people observe in spectroscopy, this zero bias peak, which tells you that your ground state is degenerate. Another measurement, which is very interesting, was done by Rockinson in Purdue University. And this measurement is, again, it's a measurement of Shapiro step, very similar to the measurement I showed you of Mullenkamp. It actually came 4 years before, but it's the same physics. And again, you can see here that in high magnetic field, there is the absence of the n=1 Shapiro steps, which tells you there was a 4 pi periodicity in the Andreev bound state. So here we are talking about SN junction in all of the other experiments, except the Lund. But here we are talking about Shapiro step measurement on a Josephson junction. And this absence shows you the 4 pi periodicity. Okay, so these works were done from 2012 and 2013. And 3 years after, in 2015, Peter's group did something which really changed the way we do experiment these days in these nanowires. And what they introduced epitaxial growth of the superconductor on top of the nanowires. So what you can see here you can see the semiconductor, the indium arsenide semiconductor, and from here you actually have an epitaxial grown superconductor. You have the aluminum growth. Now, this is actually something which is very important because it completely eliminates disorder in this interface between the superconductor and the semiconductor, and this really helps us in seeing the effect that we want. For example, a hard gap and the size of the zero bias peak itself. If I go back for a second, you can see here that all the zero bias peak were actually very small. But theoretically, we expect to see a size of this zero bias peak, which is 2e over h, as Yuval Oreg mentioned before. And this epitaxial growth is actually bringing us a step closer into this quantization. So this is an epitaxial growth on a nanowire, okay? And there are many experiments which were done in the last few years on these kind of wires. But another interesting development is that this epitaxial growth not only went in the direction of 1D, it also went in the direction of 2D. And this is by Shabani et al. And what you can see here, you can see a 2D indium arsenide quantum well, which is again proximitized by aluminum. So there is a small barrier here, but that doesn't matter. You proximitize with the superconductor the indium arsenide quantum well. Now this is actually something which is very important because if you really think about scaling up, okay, and really make a qubit out of this, you need lots of wires and you need to engineer it. And this is a bit more difficult, right, you can imagine, with nanowires, and this is exactly why this 2D approach is very desirable. Okay, so now let's go back to the ferromagnetic atomic chain. Now, up to now I was talking about a spectroscopy measurement, transport measurement. In this ferromagnetic atomic chain we are actually going to talk about an STM measurement. Now this is actually something which is very interesting because with spectroscopy we have no way of knowing that actually the state is at the end of this helical states which is proximitized. And using STM we can actually see that the localized state is at the end. So this was the idea of Bernevig and Ali Yazdani's group, which I'm going to show you now. So this is the Stm tip, and you can see the iron atoms on top of the lead, right? So it's basically these iron atoms which are organized on a line on top of the substrate. Now here you can see an AFM image and an STM image, and you can see this is basically the atoms of the lead, and they use the substrate, they use the facet of the substrate of the lead that actually when you look on it with STM, you can see that you have rows of atoms. And this is actually something very important because you want to organize the iron atoms on a row, okay? So you basically take this substrate of lead, and then you evaporate iron on top of it, and then you anneal. Now when you anneal, you are increasing the mobility of the iron atoms on top of the substrate, and then they are basically self-assembled as a line, okay? As a line of atoms, which what you see here, and this is basically this line, okay? So you can see here, this is the place that the iron was evaporated, and then you have this self-assembled line of atoms which is coming out of it. Now, what you can see on the right side, this is basically the STM image itself. So what they looked here, they basically did a spectroscopy measurement, but a spectroscopy measurement as a function of x and y. So you can see here at red, you can see the spectroscopy measurement at point 1, at the edge of this line of atoms. And in blue, you can see basically in the bulk. Now in the red, you can see this zero bias peak, which is basically telling us that there is a localized states at the end of the wire. And in blue, we can see these symmetric peaks, which are basically the Shiba state. The Shiba states are basically the states which are formed when you have a localized magnetic impurities, which is proximitized by the superconductor. So basically this beautiful technique that was developed by Ali Yazdani and was also done by Basel and Berlin basically showed us that we can locally see these Majorana zero mode or these zero bias peak at the end of these wires, these ferrite wires. Another interesting measurement this group performed is, you can see here the differential conductance as a function of x and y at zero energy, and you can see this red dot really at the end of the line of these iron atoms, which is really showing you that there is this Majorana zero mode or zero state at the end of the line. So this really shows you, the beautiful, this beautiful technique and beautiful measurement of this ferromagnetic atomic chain. So I showed you up to now the topological insulator, the 1D semiconductor, and the ferromagnetic atomic chain. In this last slide, I want to show you a bit more recent experiment that was done, different directions, which kind of opens your minds to other ways of creating the topological superconductivity phase. Okay, so the first platform that I want to show you is basically phase-induced topological states. Now the idea here is basically to have a Josephson junction, so you see here in blue these two superconductors, and you induce superconductivity on a quantum well which has a large spin orbit. So this quantum well can be indium arsenide or can be a mercury telluride not in the gap, and then you can realize this interesting physics. Now the main idea, which basically was predicted by these two groups, is that you create this Josephson junction and you create a loop between these two superconductors and you induce some magnetic field, and then you control the phase difference between these two superconductors. Now by carefully controlling the direction of the magnetic field and the phase difference between these two superconductors, these two groups in Copenhagen and in Harvard 2 years later were able to realize these physics and actually to see that you can go out and in of the topological states only by looking at the phase difference. So they were also able to look on zero bias peaks, which are evident for Majorana zero mode in these two systems. Now a second platform is also a continuation of the nanowires that I mentioned before. Here this is mainly led by Copenhagen and Microsoft, which is basically using full shell nanowire and europium sulfur ferromagnetic doped wires. So here you can see, for example, the indium arsenide nanowire that I showed you before in green, and it has a shell of aluminum. Now using spectroscopy measurement, they were able to show in Copenhagen that when you introduced an odd number of vortices inside these shells, you basically again realize this zero bias peak or Majorana zero mode physics. Another interesting experiment which comes from the same group is using this europium sulfur growth. So this is again same as aluminum. This is very interesting. It's a tri-layer junction. So you have indium arsenide, which epitaxial grown to aluminum, but also epitaxial grown to europium sulfur. And then you basically eliminate the need for an outside, an exterior magnetic field. So also here they were able to show zero bias peak signature which are associated with Majorana zero mode. The last platform I want to show you is the combination of quantum Hall effect and superconductivity. So the main idea there is basically to combine the edge states that I mentioned in the beginning in the fractional quantum Hall effect or in the integer quantum Hall effect with superconductivity. So Gilhoe was able to show from Philip Kim group in 2017, was able to show that by proximitizing superconductivity on helical states in filling factor 1, he opened the gap and he looked at cross-Andreev reflection. And 4 years later, Undergul and et al. Were able to show the same thing for fractions. And this is also something which is very interesting because this is also taking us not only to physics of Majorana zero mode, but also to physics of parafermions. Okay, so let's take a step back and really look at the different platforms that we discussed today and ask the question, what is next? And in all of these measurements, we basically showed the main thing that we show was a zero bias peak measurement, or seeing that the degeneracy of the ground state, we are looking at this degeneracy of ground state by looking at the zero bias peak measurement. And what's next? Something which is beyond spectroscopy. We want to see something which is more than zero bias peak measurement. And by this I mean, for example, a teleportation experiment, interference experiment, or braiding. Braiding is the only thing that in the end will show us that we actually have non-abelian quasi-particles that have characteristics of non-abelian, and this is really what we are after. Thank you.